This is Professor Corey, and this is the final lecture covering chemical equilibrium. In the previous lecture, we showed you how you can sometimes avoid using the quadratic equation by implementing an assumption rule, and we also did some calculations to determine a reaction quotient that was compared to our equilibrium constant to determine if we were at equilibrium. In this lecture, we will examine how making changes to an equilibrium affects the equilibrium using Le Chatelier's principle. Le Chatelier's principle involves making a change to a system at equilibrium, which can be done by adding or removing products, reactants, changing the temperature, or changing the volume of gas systems. Let's first look at the temperature effect, since we've discussed this before. This reaction has a delta H value which is negative, so this is an exothermic reaction. An exothermic reaction produces or gives off heat, so it may be useful to write the word heat on the product side of the reaction. Let's assume that the reaction is at equilibrium, meaning the concentrations of reactants and products are constant. This reaction will proceed in the direction to return the system to equilibrium. In other words, if I were to add heat to the system, the equilibrium would be disrupted as the product side is now too hot. The reaction can only run in the forward direction or the reverse direction. So in this case, adding heat, it would run in the reverse direction in an effort to reduce the heat. In doing so, the concentration of C will also decrease, and the concentrations of A and B will increase, and we call this a shift to the left. The same applies to changing concentrations. In this case, if we remove D, our equilibrium has been disrupted. The reaction will run in the forward direction to produce more D to reestablish the equilibrium. In doing so, there will also be an increase in C. In the reactants, A and B, they will decrease. This is a shift to the right. Pressure or volume changes only affect gases. To understand the effects, you may find it useful to count the number of moles of gas on both sides of the reaction, as the side with more moles of gas will be affected more by the change. Another approach is to think in terms of a reaction quotient. Let's say we increase the pressure on a closed system by reducing the volume, as shown at the bottom of the slide. To determine how this will affect the equilibrium, one can assume that the initial concentration is 1 mole per liter. This is not accurate, but if we just assumed everything was 1 molar, our equilibrium constant value would be 1. If the volume is now smaller, we could say that instead of having 1 mole in 1 liter, now we have 1 mole in 0.5 liters. Again, not accurate, I'm just making this up. But this would be a concentration of 2 molar. 1 mole divided by 0.5 liter equals 2 molar. Calculating the reaction quotient, we find the value is smaller than the equilibrium constant, meaning the shift would increase the products to reestablish equilibrium. This is an example of changing a closed system containing gases. If the volume is halved, the concentrations of the gases is doubled, and the effect would be greater on the side of the reaction that has more moles of gas. If this is not intuitive, you can use the reaction quotient approach to determine the direction of the shift. This problem has equilibrium concentrations, so we can calculate the equilibrium constant, 2.5. Realize that adding more butane will cause a shift that results in new equilibrium concentrations, but the equilibrium constant will be the same. Step 2 says calculate a reaction quotient to realize the direction of the shift, and this isn't always necessary. Like in this case, we know that the reaction will have to shift to the right to reduce the amount of butane. Where this is important is on our ice table in the change row. Notice how the ice table initial concentrations include the added butane as well. This is showing the calculation of the equilibrium constant and the reaction quotient. Since Q is smaller than K, we know the shift will be to the right, and this is needed for the change row in our ice table. Your ice table will look like this, and we can solve for x using the equilibrium constant value of 2.5. X equals 1.07, so the new equilibrium concentrations can be calculated. In the previous problem, we said that the equilibrium constant does not change, and this is true because the temperature remained constant. Here we have a reaction with equilibrium constants given at different temperatures, and there is a significant change. Since this is an endothermic reaction, we can write energy on the reactant side, or we could write heat in place of the value. The number value is shown here. If we increase this heat, the equilibrium shifts to the right in an effort to reduce this extra energy and reestablish the equilibrium. This results in the formation of more products, which increases the value for K. This is a summary of how temperature changes will affect equilibria. It may be useful to write them out in a reaction format to convince yourself of the direction of the shift. Pause the video and see if you can complete this table on your own. The answer will be provided on the next slide. If you're wondering why adding argon had no effect on the equilibrium, it is because it is not part of the equilibrium system, and therefore it will not change the partial pressures or concentrations of the other gases. This concludes our chapter on chemical equilibrium. Our next chapter is titled Acid-Base Chemistry, and we will use the concepts of chemical equilibrium and apply them to acid-base reactions. Stay tuned, and thanks for watching.